talk is by Mehdi Soleimani-far on connections between geometric polynomials and quantum partition functions.
All right, thanks for inviting. So this is based on a joint work with Aram Harrow and Saeed Mehraban. So this talk is about interacting quantum systems where you have n quantum spins on a lattice or a bounded degree graph. These spins interact with each other, and since in physics interactions are short range, basically each single spin effectively only interacts with its surrounding neighbors. So we assume the system is at some fixed temperature, and you'll leave it to evolve, and the spins interact with each other, and eventually it reaches an equilibrium state. So in physics and quantum computing, this is like a central problem. We would like to understand the properties of the systems. And in particular, we want to have approximation algorithms that, given the description of where these spins are and how they interact with each other, it estimates the certain properties of them. So the typical thing that we would like to know about these systems is their partition function. And in the rest of the talk, I'll basically tell you ways that you can look at these systems from the lens of computational complexity and approximation algorithms. Before giving you more details about what quantum systems are, let me begin with classical spin systems, which is something probably most people are familiar with. So here we assign, we have a graph, and we assign binary plus minus 1 variables to the vertices of the graph. And then for an overall configuration of these spins, there is a cost associated with them. In physics, we call this cost function the Hamiltonian. And the specific cost of like one of these configurations is called the energy of that spin configuration. So the Hamiltonian is sum of local terms. For example, it could be that like in the case of Ising model or hardcore model, each of these local terms look at the spin of connected vertices and assign a plus minus 1, plus minus jij coefficient to them, depending on whether the spins agree or disagree. And there is a probability distribution that describes the state of the system at some fixed temperature T that we usually work with its inverse beta. So one of these spin configuration is attained with a probability which is proportional to e to the minus inverse temperature times the energy of that specific configuration. And then there is a normalization factor called the partition function, which is sum of these exponential factors. So the partition function is not merely a normalization factor. It also encodes useful statistical properties of these spin systems or the combinatorial information about them. And both in physics and TCS, it's like a well-studied problem to evaluate the partition function of these systems. So I'm going to introduce some notation and like express everything that I had in this slide in a slightly different language in terms of matrices and linear algebra. And that's because it's much easier to extend that to quantum spin systems later. So now instead of assigning plus minus 1 variables to vertices, I'm going to assign vectors. So it's either a 1, 0 vector or a 0, 1 vector. So there's like a 2-dimensional complex vector space, but I only assign the basis vectors in this vector space to the vertices. And I put a ket notation on the spins here to distinguish it from what I had in the previous system. And then similarly, a general configuration of all these n spins is a vector with 2 to the n entries, and it's just because there are that many possibilities. One thing else that I do is that I put all these costs for different configurations on the diagonal entries of a matrix. So for example, if I have like just 2 spins, then I form a diagonal matrix with all the possible weights that I would assign to these two spins. So there is a more convenient way of writing this 4x4 matrix in terms of the tensor product of 2x2 matrices. So this Z here is just a matrix with plus minus 1 on its diagonal, and the index I or j is just telling which vertex this matrix is assigned to. So you can check that each the left-hand side and the right-hand side are equal. And then since the Hamiltonian of all these spins is just a sum of these local weights, I can just write it like that. And there is a tensor identity over all other spins that I usually don't write in the rest of the talk, but it's implicit there. And then similarly, I'll put all the probabilities in the Gibbs distribution on the diagonal entries of a matrix. And this can be written as a matrix exponential. So this matrix rho is just e to the minus beta times the diagonal matrix that I just defined. And with this notation, the partition function is just a trace of this matrix exponential. So far, I haven't really done anything. I've just promoted everything we had in the previous slide to diagonal matrices or vectors. But when we go to quantum spin systems, this becomes non-trivial. And in particular, there we assign any linear combination of these vectors to the vertices, and we just for simplicity assume these vectors are normalized. So it's not just anymore like one of these 1, 0, 0, 1 vectors. It could be any linear combination of them. And this is called superposition in quantum mechanics. And then similarly, the state of all spin is not one of the basis vectors among the 2 to the n possible vectors. It's like any linear combination of them. And in particular, there are vectors in this linear combination that cannot be written as a tensor product of 2-dimensional vectors. And this is called entanglement. And a simple example of that is like if you have, again, 2 spins and then their state is just like 1, 0, 0, 1, then you can't write it as like a single tensor product. You need to add at least 2 of them. So this is like kind of different from the previous picture that we assign meaningful spins to each vertex, and then the overall configuration is just like a collection of these. And then the Hamiltonian is defined as before. It's now a general Hermitian matrix, a 2 to the n by 2 to the n matrix, but it's still local. So it's sum of local terms. But now these terms, which we assign to the edges, for example, need not commute with each other. And an example of that is the following interactions. This is like very common in physics. So these are what I had in the previous slides, and x and y's are just other matrices with plus minus 1 eigenvalues, but they're not diagonal in the same basis as z. And then a and b and c's are just like arbitrary coefficients. So now if I look at the these hij's of adjacent edges, they don't necessarily commute. And as I'll describe later, this complicates like studying this quantum system. And instead of Gibbs distribution, now we have a Gibbs state, which is defined as before in terms of a matrix exponential in terms of the Hamiltonian. And it's just, again, a general PSD Hermitian operator. So we usually call this density matrix or density operator in quantum mechanics. And the Gibbs and the partition function is trace of the matrix exponential. So as I said before, this partition function is basically what we would like to approximate. And once we have that, then we can like get physical properties of the system that we would like to estimate. But exactly evaluating the partition function is known to be sharply hard. What we really want is the approximation algorithm that, given the description of this Hamiltonian, the inverse temperature beta, and an error parameter epsilon gives you an epsilon additive error to the log of the partition function. So natural question is how hard it is to approximate the log of the partition function. And this turns out to depend on the temperature or beta that you want to evaluate the partition function at. So this is a widely studied problem classically. Let me first review what we know there. So in 2 extreme cases, it's easy to see this temperature dependence of the computational hardness of approximating the partition function. at very high temperatures, meaning very small beta, the Gibbs distribution is just a uniform distribution. Evaluating the partition function is trivial. At very high temperature, at very low temperatures, meaning very large beta, this problem basically reduces to like a max CSP, which is NP-hard. So as you see, by changing the temperature, the hardness goes from being trivial to NP-hard. But we also know about another transition as we change the temperature from physics perspective, which is a transition in the phase of the system, or thermal phase transition, where, for example, we can go from a disordered phase to an ordered phase, and at a very critical value of beta, the properties of the system abruptly change. So there are various ways to characterize these phases. One is based on the decay of correlations, and one is based on complex zeros of partition function. So this picture of physical phase transition is closely related to the transition in the computational hardness. And for example, we know that mixing in time is equivalent to mixing in a space, where mixing in time means there are efficient Markov chain Monte Carlo algorithms to sample from the Gibbs distribution and estimate the partition function. And mixing in a space just means you have exponential decay of correlations in the system. So if you assume one of them, then you get the other one, which is what happens in the high temperature phase depicted above. We also have direct ways of getting deterministic algorithms by using the correlation decay. And on the other hand, we know that it's NP-hard to estimate the partition function in the below the phase transition point. And recently, there is a new method for evaluating the partition function based on the other characteristics of the high temperature regime, which is based on the complex zeros of the partition function. It's due to Barbanov. And then other people have applied it to Ising model and hardware model. And I'll describe how we can basically use the same method in the quantum setting. So okay, this was all about classical systems, but how about quantum systems? So as I said, there are various complications there. And one is that the terms in the Hamiltonian don't commute with each other. So this makes simple things like writing e to the h1 plus h2 as the product of e to the h1 times e to the h2. This doesn't hold anymore. And this causes like a direct extension of various classical methods to not be possible. And it makes quantum systems to violate like basic properties of a spin system, classical spin systems, like the Markov property. And even if you restrict yourself to commuting Hamiltonians, meaning you assume your Hamiltonian is a sum of terms that mutually commute with each other, then you can diagonalize all these in the same basis. But the problem is that the joint eigenvectors for these matrices still can be entangled. So even for commuting Hamiltonians, problem is not directly reducible to classical spin systems. And in terms of hardness, estimating the eigenvalues of the Hamiltonian, which is the equivalent of like max CSPs, is QMA hard even on a one-dimensional chain in the quantum setting. So QMA is the quantum analog of NP. But on the other hand, we don't have quantum versions of PCPs, probability checkable proofs for these Hamiltonians. And this also makes establishing hardness results harder. But despite all these complications, there has been also progress on studying this system. So as before, the two extreme cases for quantum system is the same. So at very high temperature, it's trivial to find the partition function. At very low temperature, it's NP QMA hard if beta is polynomially large, and this is because, as I said, we don't have quantum PCPs, or NP hard if beta is a constant. And from physics perspective, we still have the same picture. There is a thermal phase transition for quantum system, and the high temperature phase is characterized by the decay of correlations or complex zeros. And certain classical results have been extended to quantum settings. For example, one direction of the equivalence between mixing in time and mixing in space has been established by Brandao and Castroiano for commuting Hamiltonians. So mixing in time here means there is a efficient quantum circuit for sampling from the Gibbs state. And mixing in time means a quantum version of decay of correlations. And they've also extended the results to the general case, the non-commuting Hamiltonian case, if we further assume that the Markov property, or an approximate version of Markov property, holds for quantum systems. So as I said, this is like something that is a unique property of classical spin system, and it's always true. It's conjectured that for quantum systems, an approximate version of that holds, but so far it hasn't been proven. But we also know that there is a family of quantum Hamiltonians called sign-free or stochastic Hamiltonians, whose partition function can be directly mapped to a classical partition function. And then you can apply like existing Monte Carlo methods to evaluate the classical partition function and hence get an approximation for the quantum version. This is done by Brabi, Gosset, Crossan, Haru, and others. And as I said, there is a new method for evaluating the partition function based on the complex zero. And in this talk, I'll show you how this method can be naturally also extended to quantum spin systems. All right, so before going on, let me give you a brief overview of the results that I'll cover. So first, I'll tell you how we can get algorithms from complex zeros. And then I'll talk about the connection between these complex zeros and decay of correlations for quantum spin system. So let's start with the zeros. So similar to classical partition functions, quantum partition functions for real beta, real inverse temperature, it's just a sum of strictly positive terms. So on real axis, there are no singularities for the log of the partition function. But this changes if you look at complex betas, and in particular, in the limit of the number of particles or spins going to infinity, some of these, in certain locations, beta could be 0, and these zeros can approach the real axis and get closer and closer at the critical value of beta, which is basically where phase transition occurs. So at around this point, the log of the partition function is non-analytic, and it causes its derivatives and other physical quantities to blow up, and that's like one signature of thermal phase transition. So studying these zeros has been initiated by Li and Yang in a slightly different context, and then extended to this setup of thermal phase transition by Fisher. So our first result shows that as long as you want to evaluate the partition function at the beta which is less than this critical point, meaning it's in what's called analyticity region, then there is a quasi-polynomial algorithm for approximating it. And what do I mean by analyticity region? It basically means there is a region of constant width and length that includes beta equals 0, the infinite temperature point, such that there are no complex zeros inside this region. So if we have such a region, then the log of the partition function is analytic. But we also assume that the absolute value of log is bounded by order n inside this region. So for classical spin systems, since they're polynomial, since the partition function is a polynomial in terms of beta, we don't need to assume this. But in general, this is not true for quantum systems. So we need to have this assumption. And I'll talk about that later. So if the inverse temperature beta that we want to evaluate the partition function at is inside such a zero-free region, then there's a simple algorithm for estimating the partition function. It's just you use truncated Taylor expansion at beta equals 0. And then if you want inverse polynomial error, that means you need to only keep the order log n first terms in the expansion, which means you need to compute the order log n derivatives. So computing the derivatives of the log of the partition function can be reduced to finding the derivatives of the partition function itself. This is similar to what happens classically. And the kth derivative of the partition function at beta equals 0 is just the trace of Hamiltonian to the kth power. So remember that the Hamiltonian was sum of order n local matrices. So its kth power is also sum of terms, but now they're n to the order k many terms. And these h prime i's act on order k many spin. So if k is order log n, estimating this these local traces can be done in polynomial time, and since there are n to the order k of them, the overall running time is just n to the order log n, which is quasi-polynomial. So you can actually do better and reduce the running time to just polynomial time by using things like cluster expansions. All right, so that's the first result. It just shows that as long as you're in the zero-free region, the truncated Taylor expansion approach just naturally extends the quantum settings. But how do we actually prove the existence of such region? So we show that there exists a disk which is free of the zeros around beta equals 0 with a radius beta naught, which basically scales as 1 over the degree of the interaction graph. And the way we prove this is by recursively lower bounding the partition function using what's called the cluster expansion. So this cluster expansion is one way to get around this problem of having a non-commutative Hamiltonian. It's not the only way. And our proof idea is the following. We compare the partition function before and after adding one spin to a subset of the spins. So I forget about all the interactions. So I consider a subset of L spins, and then I forget about all interactions between other spins. And we show that the partition function after adding this new spin is lower bounded by a constant times the partition function before adding this. And once you iterate over this, then you just get an exponentially small lower bound on the overall partition function. And this just means the log of the partition function its absolute value is bounded by order n, which is what we needed for the truncated Taylor expansion in the previous slide.
So question?
Yep.
Yeah. So does this require that the graph is amenable or is like a lattice, not growing too fast?
No, as long as it's just a bounded degree graph, it suffices. I don't need it to be a lattice. It's just for simplicity. I assume that here. All right. So how do we show this lower bound on the partition function after we add a spin? That's where we use the cluster expansion. So if you've seen them, how they work for classical spin systems is similar in the quantum settings, but there are subtleties because, as I said, the local terms don't commute, and you need to be careful how you prove the convergence. But basically, these cluster expansions allow you to expand the matrix exponential in terms of this sum of the product of the local terms. And this holds as long as your beta is inside that convergence disk. So once you have this, then you can single out the effect of adding one spin to the partition function. So write the new one as the old one plus some corrections, that then you can show the corrections are basically small. And then this gives you the lower bound. All right, so these are the algorithmic results. Let me know if you have any questions.
So one more question. So can you also show something like that correlation, so that the critical activity for correlation decay and for the zeros are same in this context, in the quantum?
Yeah, I'll talk about that in our next result.
Okay.
All right, so let me move on. And yeah, now I'm going to talk about the connection between the zeros and correlation decay. So again, the picture here is not as complete as what we have classically. So for classical spin systems, by decay of correlations, like one way to characterize the decay of correlation is to look at the covariance between the spins. So we assume we have like two subsets of spins that are disjoint at some distance away from each other. And then we look at the covariance between the spins in region A and B. And as long as this covariance decays exponentially with the distance, we call the Gibbs distribution to have the decay of correlation property. So the definition of decay of correlation is similar for quantum systems. But there is also some differences. So now we consider any Hermitian operator, OA and OB, that are acting on the spins in region A and B. And instead of Gibbs distribution, we also have the Gibbs state. And instead of that covariance we have for classical spin systems, now we consider a similar expression for these matrices. So as long as OA, OB, and rho are all diagonal in the same basis, this basically reduces to what we had with the classical covariance. But in general, these are just arbitrary Hermitian matrices. They don't need to be diagonal in the same basis. And this is because the way measurements work in quantum mechanics, we have observables, and the way we have access to correlations is through these Hermitian operators. And we say that the quantum Gibbs state has the decay of correlation property if this correlation on the left-hand side is decaying exponentially with the distance. So classically, the relation between decay of correlations and complex zeros has been studied. It's proven for translationally invariant classical systems that these two seemingly different ways of talking about the phase transition are actually equivalent. And this is by Dobrashin and Schloss. And there's been extension of that to various systems that I don't get into the detail. But how about quantum systems? So we show one direction of this in certain cases. So we show that for the inverse temperature betas, that there are no complex zeros around it, the decay of correlation holds. And this is when the spins or the regions that we are looking at are at least logarithmically far away from each other, or when the Hamiltonian consists of commuting terms, or when your spins are arranged on a one-dimensional chain. So if you remember, I said the one-dimensional chain in quantum case is not like trivial. It could be in general QMA hard. So the idea of the proof is similar to the truncation, the truncated Taylor expansion that I mentioned before. What we do is that we define a function, f of beta, that measures the correlations between spins in region A and B. So this is similar to that covariance thing I wrote for quantum systems in the previous slide, but it's changed a little bit, and it's modified to have certain properties. But it's the case that if this function is small, then the correlations or the covariance I wrote in the previous slide is also small. So we can, without loss of generality, just look at this. So we show that at beta equals 0, meaning at infinite temperature, this function is 0. So this makes sense because the Gibbs state is just a uniform distribution. There is no correlation between it. But not only that, we also show that the low-order derivatives of this function are also 0. And the number of these derivatives scales with the distance between the regions that we are measuring their correlations. The further apart they are, the more of these derivatives are 0. And we also show that if at that beta, the log of the partition function is analytic, there are no complex zeros around it, then this function f of beta is also analytic. So this function looks very flat near the origin, and it's also analytic. So then we can use complex analysis tools to show that it doesn't blow up or anything if you go to a constant beta. The value of the function remains small. And as I said, the function, when this function is small, that means the correlations between the spins are also small. Yeah, so this is our results about the relation between complex zeros and decay of correlations. We don't have the other direction. So we don't know if decay of correlation implies that the absence of zeros. And as I said, this is known classically, but there are various problems in the quantum case. And they're mostly about like the boundary conditions. So in quantum settings, the boundary could be an entangled state. And you can't reduce. So one thing that is common for classical spin systems is if you have like a boundary, which are like you fixed certain spins in your graph, you can, without loss of generality, think that you've done that by flipping spins one by one. So you can look at how the system changes as you fixed spins one by one. So this view doesn't work for quantum systems because, as I said, the entanglement makes this picture of individual spins being in specific states to collapse.
So question. Sorry, one more.
Sure.
Yeah. So in the definition of correlation decay that you're using, so the prefactors, the norms of OA and OB that can scale as the size of A and B.
Yeah. So you can Yeah. So you can think of these OA and OB as Hermitian matrices with norm less than 1 if you want to like get rid of these norms.
So I was wondering. So what I was wondering is so AB are reduced spins, or they can get subspins. So I was thinking of like point to set versus point to point correlations. So this is like a point to point correlation, not point to set.
No, region A and B can contain various spins, and as you said, these norms are they're of order the size of region A and B.
Okay. Thanks.
Okay. All right. So far I've talked about the Fisher zeros, but we've also looked at the Li-Yang zeros. So the idea here is that we don't need to only restrict ourselves to beta as a parameter and like Taylor expand with respect to that. We can also extrapolate with respect to other parameters in the Hamiltonian. So this can be done for a specific family of quantum Hamiltonians called ferromagnetic Heisenberg model, where the Hamiltonian is this thing I've written here, which these X and Y and Z's are the same things in the introductory slides I had. But we also have these local Z matrices assigned to each vertex. These are like similar to what we have in Ising model, or like local fields. And the parameter that we are gonna Taylor expand with is just the coefficient in front of these local terms. So as long as the interactions satisfy this property of the ZZ interactions be greater than the ones for XX and YY, we call this a ferromagnetic system. So instead of looking at complex beta plane, you can now look at complex mu plane. And in order to do Taylor expansion, again, you need to know where these complex zeros are. And this can be done by mapping this system to a classical spin system and looking at the complex zeros of that system. So this has been done by Suzuki and Fisher. And they've shown that the complex zeros are all on the imaginary axis. So now that we know the location of complex zeros of the classical spin system, we can go back to the quantum one and directly Taylor expand the quantum partition function. So you can show that for this specific Hamiltonian, the partition function is a polynomial in terms of e to the mu. And you basically start from large value of mu, where finding the derivatives can be done in quasi-polynomial time, and then extrapolate to some constant but non-zero value of mu. So previously, there was a polynomial time algorithm for a similar model called ferromagnetic XY model. So this one doesn't have those ZZ terms that I had in the previous slide, but this is still ferromagnetic. And this is by Brabi and Gossett. And the way the algorithm works is, again, by mapping the quantum partition function to a classical counting problem, which is counting the number of perfect matchings of a specific graph. And then you can apply algorithms by German Sinclair to estimate the classical partition function and hence get a approximation for the quantum. Right? So I think I mentioned a few times that there is this way of mapping quantum partition functions to classical spin systems for certain family of Hamiltonian. I'll briefly tell you how this works. This is called like Trotter expansion. And it's again another way of getting rid of this non-commutativity of the terms. So we start with the partition function. It's like trace of e to the sum of these local matrices. And then we trivially just divide the exponent by n and then takes the n power. So nothing has changed. But then since the exponent is now, it has a 1/n factor. If n is large enough, it's polynomial in the number of spins. Then you can basically replace e to the sum of terms as a product of exponentials, matrix exponentials. And then you again have the nth power. So this kind of allows you to write the quantum partition function as a sum of positive terms. And for certain Hamiltonians, the thing that you get at the end looks like the partition function of a classical system. So there are some subtleties here. One is that this only works for certain Hamiltonian. In general, you just get a classical spin system with complex interactions. And one other thing is that if you start with a certain graph in the quantum part, what the spin system that you get by this Trotter expansion is it has like, it's in one higher dimension. So you basically take your original graph and stack it n times because of this power of n here. You stack these graphs on top of each other, and that's your graph for the spin system. And one other thing is that the spin system that you get at the end, it has coefficients on the edges that depends on the number of the spins in the quantum problem. So some of the coefficients grow logarithmically with the number of the spins. Some of the other interactions in the same spin system shrink as inverse polynomial. So it's not like a generic classical spin system that people study in TCS, but some of the sampling algorithms that exist can already handle such delicate spin systems. So this is like, for example, has been done for this perfect matching thing. So yeah, I think that's basically all I wanted to say. So there are some open questions. As I said, the picture we have for quantum spin systems is still very incomplete. We don't have the equivalent of various results for classical spin systems yet. In particular, it would be nice to have a stronger results on the complex zeros, their connection with correlation decay, or get just better algorithms for quantum partition functions. One other thing is that I think this is like a good opportunity for people in TCS to apply their toolkits to solve quantum problems by using this mapping. So normally, as I said, the classical spin models that you get via these mappings is not like something that is motivated by itself. So people probably haven't studied it in the past. But maybe the same techniques that already exist for conventional spin models can be extended to this system. So I talked about how quantum partition functions can be mapped to classical spin systems, but there are also other quantum problems that you can analyze by looking at spin models. And these come from quantum circuits. So you can, I don't get into the details, but you can look at these papers. The basic idea is that you can map the output probabilities of quantum circuits to partition function of spin models with complex interactions. So there are recent results for studying these spin models with complex interactions. It would be nice to apply them to these quantum problems. All right, so with that, I'll finish my talk. These are the references. And thank you.
Thanks a lot. Questions?
This is one quick question. Sorry, yet again. So the Dobrushin-Schlossman condition. So it requires some kind of slow growth of the graph, right? The graph should not be growing too fast. So I mean, they stated for lattice,
Right.
but you can. Yeah. So does your result also your result that the zero freeness implies correlation also require, yeah, it does, because of this trace A, like the OA scaling as the size, I think.
Yeah. So the results that I presented, they almost all of them work for bounded degree graphs, or like there is this notion of as you said, the small growth of graphs, which basically asks how for any spin, how many interactions or how many edges are connected to it, or like if you have a hyper interaction graph, then a similar condition. Also, for our results also apply to that.
No, in the sense that so what you're asking is that, so if the graph is growing faster in the lattice, if you look at a distance L, there are only like the number of neighbors that you have grows polynomially in L, whereas in a random graph it grows exponentially in L. And so in the correlation decay condition that you had, because of this dependence upon OA, if the distance itself, like at distance D, if the size, the norm of OA itself is growing exponentially, so then you don't get full correlation decay. So it's in those graphs you don't get, but in lattice, such a thing can never.
Right.
So
correct.
So because the Dobrushin-Schlossman, I think, also has the same restriction, that it requires this, and so the same restriction goes over here as well.
Yeah. So I mean, even as I said, we still can't get exactly the same Dobrushin-Schlossman result, even with that limitation, because we assume that the spins need to be at least logarithmically far away from each other. So we can remove this restriction.
Log n far, right.
So yeah. So I don't.
But as soon as you get log n, you start getting exponential decay from there on. So
correct.
It's like sort of.
So there is a factor of n in front of the exponential.
That's very.
And classically, you can remove that by using Markov property. As I said, quantumly, that just breaks.
Yeah, thanks.
Any other questions? Okay, thanks again to all the speakers today. We're going to reconvene tomorrow. Have a good rest of the day. Bye.